So with that, I'm going to switch seats with Lou, and I'm going to let him start his presentation. So thank you all again.
All right, thank you, Tom. Everyone, I appreciate you jumping on the call this afternoon. My name is Lou Battaglia. I am a systems sales engineer with New England Train, located in Wilmington, Massachusetts. Tom had asked that is not a photo of me on this first slide here. That's our generic train technician. So if you could see me, hello, everyone. But Tom invited me in here today to talk to you all about air handling systems. Air handlers are some of the most complex pieces of equipment in your mechanical room. They come in all shapes and sizes. So this is not a comprehensive introduction to air handling at all, more of an air handling 101. But I encourage you all, if you have any questions, feel free to use the chat. I'll also open it up for Q&A towards the end. I'd like to keep this interactive, so if you see anything on the screen that you'd like me to go into a little bit more detail, feel free to stop me throughout the presentation. I don't think this should take the full hour, so we should have plenty to open it up. So with that being said, start our presentation here. And just to give you a little bit of an overview of what we'll be discussing, we'll start by jumping into the drivers of air handler selection. These are the questions that an engineer will ask a building owner or a facilities director about their building, about what they need out of their air handlers, to talk about climate, things like that. Basically, the main drivers that indicate how an air handler comes together. Next, we'll go into some of the air handling system components. So you can think of these as the individual building blocks of an air handler, your fans, coils, filters, and there's many more modules that we'll hit on. And once we go over the individual building blocks, we'll talk about how the blocks come together in the different types of air handlers. Some of the main types of air handlers that you probably heard about are your catalog units, you have your modular or semi-custom units, you have full custom units, and even package DX. And once again, we'll open up the floor to a Q&A at the end of the presentation to answer any questions that you might have or you haven't been able to get into the chat. So with that being said, we'll kick it off by going into some of the drivers of air handler selection. So at the beginning of any project, when you're working on either a new square footage of a building or renovation, or if you're using existing equipment, and all the way, we're going to work with the building owner to and a few different criteria on what they need out of their air handler. Some of the primary.
Close up higher. Come on.
Excuse me, I'm sorry to interrupt. Please, who's ever on the phone there, you need to mute your sound. Thank you.
Sorry about that, guys. But so once again, the engineer is going to talk to the building owner or facilities director about different criteria, what they need out of their air handling equipment. Some of these questions revolve around the duty or function of the unit going to be providing cooling? Does it provide heating? Does it need to have some form of energy recovery? Does your space have some kind of humidity control requirement, whether it be dehumidification or humidification, or if there are certain sound requirements? So acoustics, you think of labs, libraries, any building where you might have a need to have very quiet sound levels in the occupied space. Then the next question that comes into play are what type of resources are available. The resources that we're referring to are your chilled water or hot water, if you have steam on site, natural gas, propane, or even electricity. These are the means that allow the air handlers to perform either cooling or heating duty. The next question that we'll dive into is the vertical market, or what kind of facility is this unit being applied in. An air handler that is built for a healthcare facility or for a school, college, is going to differ in configuration, components, even construction quality, depending on the project. So no two air handlers are built the same. Each different vertical market has certain requirements that need to be met in order to have a valid application. Last, we're going to have the building architecture or construction. So if it's a new building, you might have a little bit more space to physically get air handlers into a mechanical room or up on a roof. If it's an existing building, it's probably a little bit tighter, so you need to make sure that your individual sections can be brought into the mechanical room. Additionally, if this unit's going to be located indoors or outdoors, there's going to be certain questions that an engineer asks in terms of what kind of lifespan you expect out of these units to determine if you want to go with a galvanized or stainless, aluminum, so on. Also, things that come into play are the region or climate. Different areas of the country have different requirements by ASHRAE in terms of components that need to be included, as well as your budget. You can definitely build an air handler on a budget-conscious project, or you can build a robust air handler with redundancy and construction enhancement that can make it a 20 or 30-year unit. So these are all the questions that an engineer, even a salesperson like myself, might ask a building owner. What do you need out of this unit as you're moving forward in the construction project? And once you have an idea of the answers to some of these questions, you can go ahead and start picking the individual components that are going to make up that air handling unit. So as we back it up a few steps, I just want to tell you what the definition of an air handler is on our end of the spectrum as an equipment vendor. So an air handling unit is a piece of equipment that regulates and circulates air as part of a heating, ventilation, and air conditioning system. On the right-hand side, I have a basic picture of an air handler, and some of these components that you're going to see in almost every unit include your dampers, which regulate how much return air or outdoor air enter the unit, filter racks that are used for filtration, cleaning out the air, preventing particulate matter from entering the airstream. You have your heating and cooling coils, which temper the air, whether you're in the winter heating season or summer cooling, and your fans that physically move the air throughout the system. But this is a very basic unit, and they can get complex quickly. So as we go forward, let's take a quick look at some of these components and how they might differ from unit to unit. So the first component we'll take a look at is filtration, filters. I'm sure everyone understands what a filter is, but filters come in all different shapes and sizes depending on what type of application you have. So some of your standard filtration options would include pleated media, which would be your MERV 8s or MERV 14s. The MERV is an efficiency rating that is used to compare how much particulate matter is removed from air passing through a filter. So a MERV 8 will have a lower level of filtration than a MERV 14 or MERV 17, for instance. And that being said, you can also go with different types of filters. So you have your standard pleated media. You could go into a bag or cartridge filter, which are going to be longer in length, typically 4 to 12 inches, and they have MERV ratings between 11 and 15. And you have HEPA filters, which can go up to a MERV 17 rating. The nice thing about, or the important thing to note about filters is that it's important to control contaminants and gaseous particles in your airstream to have a comfortable occupied space. So you can do this by having more filters. It has effects on your fan performance. You need larger fan horsepower to push air through bigger filters, but it does result in a cleaner, more comfortable occupied space. Another thing to keep in mind when looking at filters is there's a variety of ways that they can be mounted in an air handler. You can have an angled filter rack versus a flat. So in the top right-hand corner, you see this angled filter rack where the filters are in an almost sawtooth pattern. Alternatively, you can have a flat filter rack. So you might ask yourself, why would you use an angled versus flat? An angled filter rack uses more filters. It increases the effective surface area of the filter, which in turn means it's going to take less fan energy to pull that air through the filter. One downside of that is an angled filter rack is going to take up more space. So that's something to consider as you're designing your air handler. An angled filter rack, you'll change your filters less frequently. A flat filter rack takes up less space. So it's one of those questions you say, can I afford an extra 12 inches, 18 inches in my air handler to go with an angled rack versus flat? Another aspect of mounting for filters is your side load versus a front load. So you might be more familiar with a side load filter where you're opening a door on the side of the air handler casing and you're physically sliding the filters in and out of a rack, a 2-inch rack, 4-inch rack. There's also filter mounting called front load, which is you have to step physically into the air handler and remove the filters from the front load rack using gaskets and clips. Front load filters require more space because you physically need to get into the air handler to remove them, but they do provide a better seal around the edges of the filter so less air bypasses the filter. You basically ensure that all air is going to pass through that filter and remove any particulate or gaseous contaminants. So when you're designing these air handlers, there's a couple different considerations you need to take place. Filter efficiencies versus cost. Filters with higher MERV ratings, so your 14s, your 17s are going to cost more, but they will have better particulate filtration. You also have to look at your airflow resistance. So anytime you add more filters to a unit, it's going to increase the amount of fan energy required to move that air through the system. And then lastly, the footprint. So like I said, you can go with an angled filter rack or a front load filter rack that might give you better pressure drops or better seals around your gaskets, but it does add length to the unit. The next component we'll look at is what's called a catalytic air cleaner. So certain applications have requirements to reduce VOCs in the airstream. So think of things like hospitals or waiting rooms or any type of facility that might have engine exhaust. And for situations like this, Trane has a system called a catalytic air cleaner. And a catalytic air cleaner, or TCAX, combines 3 different air cleaning technologies, which are particulate collection with a MERV 8 or MERV 13 filter. We also use high-intensity UVC lights, and then photocatalytic oxidation, or PCO. So the combination of these 3 filtration techniques reduce the VOCs in the airstream and airborne biological contaminants, so your viruses, bacteria, fungi, and mold. All these reactions take place within the air cleaner, so there's no byproducts that get emitted to the airstream or that need to be expelled from the unit. And like I said, this is ideal for any type of application where you might have some airborne bacteria, like your hospitals, waiting rooms, or facilities where there's noxious gas, like a maintenance facility that might be serving buses or trucks. Next in the unit, we have your cooling and heating coil. So this is an integral part of almost every air handler that conditions air. Your cooling and heating coils are going to be the main force that temper the air in the airstream. And the construction is most commonly copper tubes with aluminum fins bonded to them. So you use copper tubes with very thin aluminum fins to maximize the amount of heat transfer between your coil and your cooling fluid and the air. You can also have galvanized or stainless steel coil casings. So your stainless steel coil casings are going to be used in any type of application that might have a corrosion consideration. So stuff that's by the ocean, or stuff that you might, or applications that have spray dryers, things like that. You can also have epoxy coatings for corrosive areas. So that is an epoxy coating that goes on the entire coil surface area, which further bolsters the corrosion resistance. Your coils can typically be selected between 1 and 12 rows, and then the number of fins that you'll see is between 80 and 160 fins per inch. As you add more rows to a coil and more fins, your air pressure drop is going to increase, which then further increases the amount of fan energy required. So it's on design engineers and system sales engineers like myself to find the right balance of a coil for pressure drops and heat transfer, as well as cost. We also have something that's called a face and bypass coil, which is shown on the bottom right-hand corner. So these were typically used in steam applications or older hot water applications. And on these coils, you have a face and bypass damper. And this face and bypass damper allows the coil to bypass some air around the coil and send some air through. So you have a mixing strategy of conditioned air as well as bypass air in order to meet your discharge air temperature. Face and bypass coils have largely gone to the wayside now as the control strategy for valves has increased over the years, but you still see face and bypass coils used in some steam applications or areas where you don't want to send all that air through your coil during all scenarios. Now, when selecting coils for an air handler, there are a few service considerations that you want to keep in mind. Coils need to be periodically cleaned in a unit, so to do that you need to have access sections upstream and downstream. You also want to have room to mount control components, so discharge air sensors, low limit switches, things like that. So if you don't carve out room for your air handler in design, it's going to be a nightmare for your maintenance people to get in there and clean coils or replace control components when things fail or get dirty. Another consideration is your coil pull clearance. So in the event that a coil tube bursts, you're going to need to physically pull that coil out of the side of the air handler. The coil pull clearance required for most air handlers is going to be the entire width of the coil. So if you have that air handler jammed up against the wall, or if you have a beam or another piece of equipment very close, you might sacrifice that ability to remove the coil from the unit, which is going to be a pain in the event of a coil failing. Another consideration would be pipe cabinets or pipe chases or even dog houses, as you sometimes hear them called. A pipe cabinet is a cabinet that sits on the exterior of an outdoor unit, and that allows you to house your piping connections as well as any valves or pressure or temperature gauges in an enclosed box so they're not out on the roof seeing the elements or run the risk of freezing. So these are a couple of considerations. An engineer will definitely bring them up with you as you're planning to allot space in a mechanical room or a roof for your air handler project. In addition to cooling and heating with chilled water, hot water, you can provide heat via gas or electric. This top left-hand corner picture is a gas heat module, and the bottom left-hand corner is an electric heat module. And your gas heat is going to be ideal when you're in a situation you have climate with a large heating load, or if you have a building that doesn't have a central boiler plant with hot water or steam available, or areas that just have inexpensive natural gas. So your gas heat, you'll see things like turn-down capability, and that's the ability of a gas heater to modulate your gas input to match your heating requirement when you're not at full airflow. So typical turn-down capacities you might see are 2.5 to 1, 4 to 1, 12 to 1, 20 to 1. The more turn-down you have, the tighter control you're going to get on your gas heat, but the more expensive the gas heat module will be. Some things to consider when using gas heat in a unit is that the gas heater must be applied in a blow-through configuration. And when I mean blow-through, it's that your fan is the first in the airstream and it physically blows the air through the gas heater. And this is required because you don't want any of the combustion gases to enter the airstream and then get sent to the conditioned space. With electric heat, it's a very inexpensive first cost option. You can see that it almost looks like a toaster element in your airstream. It's inexpensive as you don't need any separate gas or hot water or steam piping. Every site is going to have electricity available, so if you don't have hot water or gas, it's a good application to use. Electric heat is nice because you can do it in a blow-through or a draw-through configuration. Draw-through is when your electric heater will be first in the airstream and the fan is physically pulling the air through the gas heater. And one of the drawbacks of electric heat versus gas or hot water is that you have lower heating capacities available compared to gas, hot water, steam. So think of electric heat. The more heat you need, the more electricity, and the more electricity, the bigger your wiring, the bigger your electrical breakers, components, fuses will be. So it is one of the trade-offs when using electric heater as opposed to gas or hot water. I mentioned earlier, some projects have a certain humidification requirement. So as you all know, in the wintertime, buildings tend to dry out. Your skin can get dry, can crack. Certain laboratory applications have a humidification requirement for them to produce or to manufacture a product. And in these scenarios, we'll put a humidifier in the air handling unit. So on the right-hand side, you can see these humidifier grids. They can come with vertical or horizontal dispersion tubes. So these are the tubes that physically introduce the steam to the air to allow the air to pick up the moisture. So humidifiers use low-pressure steam to add moisture to the air. It can be accomplished either using building steam, which is pressurized, or atmospheric steam, which can be generated almost like a tea kettle scenario. Application considerations when using humidifier are that the air must be horizontal and relatively uniform across the grid for even distribution. And when we say uniform velocity, we're looking at 400 to 700 feet per minute across the humidifier. Those typically fall in the ranges of what you'd be sizing a cooling coil, so as long as your cooling coil is sized for correct face velocity, your humidifier should fall in line. You want to locate a humidifier downstream of any filters or gas heat or electric heat sections, just because you don't want those modules picking up moisture that might not enter into the air or disperse in the air completely. And you also don't want to have a leaving relative humidity off your humidifier greater than 83%, because you could run into issues with condensation downstream. Also, every single humidifier has a required dispersion distance that allows the air to dissipate or allows the moisture to dissipate into the air before hitting any downstream components. So that'll be an item that's called out in your air handler selection on the humidifier. It will say 12 inches downstream of uninterrupted space required for proper air dissipation. Next we have our fans. So fans are basically the heartbeat that moves the air throughout the system. They come in a lot of different shapes, sizes, and configurations. And a couple of the main ones that we'll see in an air handler are your centrifugal fans, your direct drive plenum fans, or motorized impellers. So on your right-hand side here, this first picture of the blue fan with the yellow housing is a centrifugal fan. And then on the right-hand side, you have two direct drive plenum fans in a stacked configuration. And on the bottom middle picture, you have a motorized impeller fan. So each of these fans has different strengths and weaknesses that we're going to dive in the next couple of slides here. But first, I want to take a look at another term that you'll see revolving around air handling fans are housed versus unhoused fans. A housed fan has this box around it, physically called a housing, that directs the air into the inlet of the fan, and then the centrifugal fan shoots the air out radially in a direction, versus an unhoused centrifugal plenum fan takes air through the beginning of the fan impeller, and then it pressurizes the box. So you could think of it as a centrifugal fan throws air in a certain direction, versus a plenum fan pressurizes the box, and then the air escapes through any type of opening or damper. So a plenum fan is going to be more commonly used in large air handling units where you have to move a lot of air at a high static pressure. And as we look at the different types of fans here, the first fan we'll look at is a forward curve fan. A forward curve fan has fan blades, so this picture on the left here is actually a side view of this fan wheel. And you can see this black line is the fan blade. So it's aptly named forward curve. Forward curve fans usually run at relatively low speeds, and they deliver large volumes of air at relatively low static pressures. The fan wheels are very light construction, so the FC fans typically cost less than fans with different blade types, and they're most commonly used in smaller systems that require static pressures roughly 4 inches or less. The nice thing about FC fans, they have a very wide operating range. They have very low surge characteristics, so your fan doesn't have to worry about running in an unstable operation point. When fans are operating in surge, you're going to get unstable airflow, static pressure, as well as acoustics. These are very forgiving fans, as they don't have a surge line that's as severe as an airfoil or a backward incline fan. So FC fans, because they're very forgiving, they have less costly construction, you typically see them used in packaged rooftop units where not as much consideration is taken into duct design. If you have a retail shop that's replacing an existing unit, they might not take a full look at the supply and return duct static pressure requirements. The next fan that we have available to us is a backward incline or a backward curve fan, your BI or BC. So this first fan we see here is the backward incline. Once again, the backward incline refers to the shape of the fan blades, or this is backward curve, or below you have your backward incline fan. These fan blades are shaped away from the direction of the wheel rotation, and they have a much more rugged construction than your FC fan that we saw earlier. So these fans can operate at higher speeds, making them more suitable for high pressure, high airflow applications. They typically tend to be more efficient than an FC fan, but they have a more severe surge characteristic. So as I mentioned, surge is when your fan gets into an unstable operating range. So greater care must be taken during your duct system design to ensure proper static pressure calculations and make sure you have the right fan selection for your job. The last different type of fan blade we'll look at is an airfoil fan. And an airfoil fan changes the flat blade we saw earlier from the backward incline to an airfoil shape. So this is more similar to an airplane wing. Your backward incline fan or your airfoil fan is going to be the fan that can operate the highest static pressures and airflows, and it's more efficient than other fan types. But these do come at a higher cost of the fan wheel, so you'll typically see these used on custom air handling units or any type of mission critical scenario. And this all culminates in what I want to describe as the direct drive plenum fan, which is going to be one of the standards that you see in fan selection for air handlers nowadays. So a direct drive plenum fan uses a fan that has the fan motor directly connected to the fan shaft. Historically, in a lot of HVAC applications, fans would have a drive kit consisting of belts and shivs that connect the fan motor to the fan shaft. So with any type of belt and shiv, that's going to require periodic tensioning, replacing of the belts, just more maintenance versus a direct drive plenum fan where your fan shaft and the fan wheel, or the fan motor shaft and the fan wheel are connected to a single assembly. The way these fans operate is usually through the use of a variable frequency drive that allows the fan to operate at different RPM, thus changing the airflow and the static pressure characteristics. And there are fewer moving parts, so you don't have any belt-related drive losses. There are less inlet and outlet obstructions. They're typically more efficient, quieter, and experience less drive and less vibration than your forward curved or your housed fan. And because the motor is in line with the direction of airflow, the motor is mounted behind the fan wheel. It doesn't restrict the airflow. It doesn't stick in the side of the unit, and it doesn't increase the unit width. However, the unit might be slightly longer because your fan motor is going to be downstream of the fan wheel, so you want to incorporate that length into your fan selection in the air handler. And one of the newest types of fans we're seeing used in HVAC applications is a motorized impeller fan. So a motorized impeller uses that same impeller that we saw used on the direct drive plenum fan, but it couples it with an electronically commutated or an EC motor. You see these called ECMs as well. And ECM is a turnkey package which includes the fan, the motor, and the motor controller all as a single assembly. So you eliminate the need for a VFD. It reduces the price. It's easier to configure EC motors to work from the factory versus a VFD, and they have a very compact footprint. In the bottom right-hand corner of the screen, you can see an air handler with the ECM fans, and the fan and the motor take up a very small amount of room compared to the DDP or the housed FC fans we saw earlier. One restriction on these is that you have a fewer selection of fan sizes and motor KWs available, as well as they don't operate well at high static pressures. So if you have a low static pressure or a small CFM unit where you do want to vary the fan speed and the amount of airflow supplied, motorized impeller fan with an EC motor would be a great option to consider. So now that we've gone through and looked at all the different types of fans that you can have, let's talk a little bit about fan application. So if you ever worked with an air handler before, you know that there are different types of fans, which can be your supply fan, return fan, or an exhaust or relief fan. And you might ask, why do I need all these different types of fans in my system? So your supply fan is the primary means of circulating air throughout the air distribution system. Every air handler will have a supply fan. Not all air handlers have return fans or relief exhaust fans, but they might be an option to consider depending on what type of application you have. So the difference between a return fan, which you can see in the top right-hand corner, this is your return fan supply, and then an exhaust fan, which this is your exhaust fan and your supply. The return fan operates continuously while the supply fan is running to balance the amount of air supplied to and exhausted from the space. Return fans are used in systems that have high return duct static pressure because it reduces the power requirement of the supply fan. So if you have a fully ducted return from your space, it's going to require a lot of energy for a single supply fan to move all the air through that distribution network. Using a return fan reduces the supply fan horsepower required. So you use smaller motors. If anyone's ever tried to pull a motor off of a fan, they know that it's a lot easier to pull a 5 horsepower motor than a 25 horsepower motor. So that is one of the benefits of using a return fan. But keep in mind, a return fan is going to run continuously while your supply fan is running. Now, alternatively, you could use an exhaust or relief fan. Exhaust or relief fans are the terminology is used interchangeably in our industry. And an exhaust fan modulates from full capacity when the air handler is in 100% outside air mode, or as we call it, an economizer, to off when the unit is in minimum outside air. So this exhaust fan is used to expel return air from the space to the outdoors, and they use these outdoor air damper to pull more air into the unit to send to the space. Now, the difference between an exhaust fan and a return fan is that the exhaust fan is only going to run when the unit is running above the minimum outside air condition. So with an exhaust fan, as we described earlier, your supply fan is still sized to handle the full static pressure of the supply and return ductwork. You get no relief on your supply fan horsepower when using an exhaust fan because the exhaust fan isn't continuously running like the return fan. The nice thing about it, or a nice thing about our exhaust fan, is that you don't have to run that fan 100% of the time, so you can allow the supply fan to run at a more efficient operating area versus a return fan where you're running at a lower horsepower. And I did mention it on the previous slide, but another component I'd like to address is an economizer. An economizer is a module that reduces the energy consumption of your air handler by enabling free cooling. And when I say free cooling, what I mean is in certain scenarios, your building might require cooling when your outdoor air is a favorable condition, let's say 65 or 55 degrees outside. So in these scenarios, you don't want to return the warm 75-degree air back to the space because you can take advantage of the cooler outdoor air. The economizer is going to monitor your return air and your outdoor air temperature and humidity and modulate the dampers to take advantage of favorable outside air conditions when they occur. Now, I mentioned that economizer looks at humidity and temperature. There are a few different control strategies for economizers that you might see. And these include your dry bulb economizer control, which only looks at the dry bulb temperature to a fixed dry bulb temperature set point. You also have your reference enthalpy. So enthalpy is a combination of temperature and humidity. It's the overall energy level of the air. So reference enthalpy will compare the outside air enthalpy, which is the temperature and humidity, to an enthalpy set point. And lastly, you have your comparative enthalpy, which is the most accurate use of free cooling, where you're directly comparing your outdoor air enthalpy and enthalpy to your return air enthalpy to determine which airstream has a lower energy requirement and which airstream is going to take less energy to return to 55-degree supply air. Now, this unit up top, it has an economizer module on it. As you can see, it does take up a large amount of room because you need to have dampers that allow you to exhaust all of your return air as well as pull in 100% outside air. But one thing I'd like to note is that with all things, there are caveats to the requirement of economizers. Up here in New England, economizers are required if your system is greater than 11 tons. You'd think that it would make sense that you want to be able to take advantage of the favorable outside air so you can shut down your compressors, you can shut down chillers, and you can supply cold air without any use of mechanical cooling. But in certain areas of the country, like the southeast, where the temperature is so humid throughout the year, economizers are not required by code. So depending on where your project is located, you have to analyze whether or not you need economizers or some other modules that I addressed previously in the presentation. Now, another strategy similar to an economizer is an energy recovery strategy. So these are used by wheels or fixed plate heat exchangers, and you typically see energy recovery utilized in applications that require 100% outside air. So these are facilities like hospitals, labs, arenas, theaters, or even maintenance facilities. So each one of these facilities has a different reason that they want 100% outside air and no return air back in the space. With your hospitals and labs, you might have bacteria or gaseous contaminants in the air that you don't want to recirculate back through. In arenas and theaters, each person that's in an occupied space has a certain outdoor air requirement. So if you think of TD Garden, or if you think a theater where you're going to have hundreds of people in that space, during certain scenarios you will require 100% outside air application. Or likewise a maintenance facility where you might be working on trucks or buses, you can't recirculate any of those gaseous fumes back in, so you're constantly bringing in 100% outside air into that space. So a couple different ways that you can recover energy from that cool exhaust air and temper the hot outdoor air are an energy recovery wheel or your fixed plate heat exchanger. So in the top right-hand corner, we have a picture of our energy recovery wheel, and the way this wheel works is you're going to send return air from your space. So consider, let's think about a hospital. 70-degree air from the operating room is going to pass through this return air wheel and exhaust to the outdoors. And then on a hot summer day, you might be bringing in 95-degree outside air, and it's going to pass through the supply side of the wheel. So this wheel spins very slowly, and it's made of an energy transfer material that allows the wheel to pick up heat and cooling and pre-temper your supply air, so you're basically saving some of that cool air off your return airstream and passing it on to your supply air. It provides a little bit of cooling before you have to use your compressors, your chiller, and your coils in the airstream. Another option would be a fixed plate heat exchanger, which is shown below, which is very similar. This is comprised of that don't provide any amount of cross leakage. So if you don't want contaminants from your exhaust airstream passing in your supply airstream, you use a fixed plate. And like I said, once again, it's going to temper your supply air to a cooler temperature before sending to your coils to provide the rest of the cooling. So some of the benefits and drawbacks with an energy recovery wheel: you can transfer both heat and moisture. So in the wintertime, your energy recovery wheel is going to add more moisture to the air so it isn't as dry. It does allow a bit of cross leakage between the airstream, so there is some consideration that needs to be accounted for whether or not you can have cross leakage. It's a self-cleaning energy recovery strategy, and what that means is that as any particulate passes through the return air side, it will get picked up in the supply air and then filtered out by filters downstream of the unit. But this wheel does have a belt and a motor, so it does require some periodic maintenance to tension that belt, make sure the motor is operating as properly. With a fixed plate heat exchanger, you only have sensible heat transfer. Now, I do have an asterisk on that. There are some fixed membrane heat exchangers that allow moisture to pass through, but we see them very rarely used. There is minimal cross leakage or no cross leakage between the airstream, depending on what the plates are made of, but these are not self-cleaning and they have a larger footprint than the wheel. So we typically see them used in applications such as residential, where it's very small air handlers, or any type of application where you might need no cross-contamination of the two airstreams. And last but not least, we have a couple other miscellaneous components. These are more specialty components that you will see few and far between in some air handlers. And these include attenuators, blenders. An attenuator or silencer, which is shown in the top left-hand corner here, uses a dissipative material, so like a mineral fiber covered in a perforated liner to prevent airflow erosion. And it reduces sound transmission sent to the occupied space. So if you have an application like a library or a classroom or a theater where you need very low sound levels in the space, you can have an attenuator or silencer in your air handler, or it's common to see these in ductwork downstream of the unit. You also have things like blenders up here in the top right-hand corner. A blender, what that does is it mixes two airstreams. So if you have a very cold outdoor airstream and then you have return air from the space, if you send those into the air handler, there's this item called stratification, where your cold air is going to sink to the bottom of the unit and your warm air is going to rise to the top. So if you send that stratified air to a coil, it's not going to temper all the air evenly. A blender, what it does, very similar to the name, it takes the two airstreams and passes through these baffles, and it physically mixes the two airstreams, so you have one uniform airflow and temperature prior to hitting your coils, filters, fans, things like that. And last, we have a plenum. Plenums are commonly used for your return or supply air. So as I mentioned before, this plenum fan, it pressurizes a box. So this eighth module is going to be pressurized, and the air is going to escape through any opening or damper. So as the pressure builds in this box, the air is going to pass through this top opening. The plenum allows the air to expand rapidly, so this reduces the air turbulence and sound. Once again, if you have a direct drive plenum fan with a sound-sensitive application, it might make sense to use an attenuator, a silencer with a plenum to reduce the amount of transmitted sound to your occupied space. So that covers most of the components you're going to see in an air handler. Like I said, there are some specialty components that might make it in from time to time. This isn't a comprehensive presentation by any means, because this is the most complex piece of equipment used in your HVAC system. But now that we have an overview of the different components or building blocks that make up an air handler, let's take a quick look at the different types and how they might be applied in your facilities. So the primary types that we see are your catalog units, your modular or semi-custom, fully custom units, or even package DX. So as we can see down here, this Trane UCCA unit is our catalog air handler, small unit with limited component selection for budget-conscious applications. You have these custom units. As you can see here, this unit comes in all different shapes and sizes. And then you have your package DX, which are going to be your more traditional package rooftop units. To start us, we'll take a look at these catalog air handlers. So when we first did this catalog, I think the nomenclature was that you could physically open a catalog and scroll down and pick an air handler out of the page. So it's a very, very pre-packaged solution. They come at smaller airflow ranges, usually 1,000 CFM to 1,500 or 15,000 CFM. They have fixed casing sizes, so fixed aspect ratios, and fixed component selection. So it might be limited to 2-inch or 4-inch filters. For coils, you'd be looking at hydronic, DX, or electric coils. And for fan options, you typically see them with direct drive plenum fans or your impellers with ECMs or your electronically commutated motor. They're available in indoor and outdoor units. They can be shipped as a single piece, so you don't have to assemble an air handler on site. And they're ideal for any type of budget-conscious application, so things like K through 12 for small offices or retail where you don't have very specific requirements in terms of filtration or sound. This is a great unit to look at. It's going to have the shortest lead times, lowest cost, but least amount of flexibility. And as we can see here, this is an exploded view of our UCCA, and as we walk through, we have your mixing box with an angled filter rack, your coil, your direct drive plenum supply fan. This unit uses a 2-inch double wall foam injected casing, so it is a very rigid casing with very good thermal characteristics. You're not going to see condensation or any kind of sweating on the exterior of the air handler. Over here we have our low voltage controls enclosure, so that's where you're going to see your unit controller that tells the fans to ramp up, coils to modulate, things like that, as well as your variable frequency drive, which physically ramps the speed of the supply fan. And the next unit we have in our portfolio would be a modular or a semi-custom air handler. Modular meaning that the air handler is comprised of different modules which then get assembled on site. These can be built anywhere from 1,500 to 120,000 CFM. They're stackable and they have a building block design with hundreds of components and countless configurations. So this is the flagship model that you'll see 90% of construction projects. Very flexible. It has 2-inch, 4-inch, 12-inch, 18-inch, or even 30-inch filtration options. For coils, you can use hydronic, DX, electric, gas, or and gas cooling and heating options. And for your energy recovery, you can use the wheels, the plate and frame that we spoke about earlier. You can have glycol energy recovery. These units can be built for humidification or dehumidification capability. For service, you can include things like access sections, lights, convenience outlets. So you have a 115-volt receptacle on your unit for a service person to go in there and use a drill or set up a laptop. Once again, these can be configured for indoor, outdoor construction. And we typically try to ship these as a single piece when possible. It limits the amount of on-site assembly required, but we can provide shipping splits if you have to get these through a tight door in a mechanical room, or if you have to bring them up on an elevator lift. We can set these up to be shipped in smaller sections where need be. So as I said, this is our flagship air handler. It's going to be ideal for any type of robust application. So you can see these used anywhere from hospitals, higher education, any type of library, museums, large offices, arenas, hotels, airports, etc. And really these can be configured to be basic or as complex as need be up to a certain limitation. So just to give you an idea of where catalog and semi-custom units are applied, here's a pie chart. These are Trane estimates, so this might not be the de facto distribution across the country, but this is what Trane sees in our portfolio of distribution. The vast majority of our catalog and semi-custom air handlers are going to education vertical market. You see 12% being used in a government setting, 16% in healthcare, 15% in your industrial, 3% in retail, another 3% in commercial lodging, 18% in commercial office, and 1% in your other commercial spaces. So definitely your education, healthcare, government, industrial, and the office space are going to be taking up the lion's share of the market share for catalog and semi-custom air handlers. And here's just a couple pictures I'm going to show you of these modular units. So as I said, these come in shipping splits, which then get assembled on site. So this is a large 50,000 CFM outdoor unit. It's actually installed at a facility in Acton, Massachusetts. And this unit had to be broken down in shipping splits because, as you can see, it was physically too large to fit a single unit on a flatbed truck, or it'd be too large to pull these up to the roof via the crane. So they come in these sections, and they land them on a curb, and then they get field assembled to build a final air handler assembly. And then another use of a modular semi-custom unit, so to show you how complex they can get, this is a stacked unit. It handles 100% outdoor air, and this is a unit that's used for humidification and dehumidification control for a manufacturing facility also in Acton, Massachusetts. So walking through this air handler, your supplier is going to, or your outdoor air handler is at the top, passes through your filters, your heating coil. This wheel here is called a CDQ, which it stands for cool, dry, and quiet. The air gets to your supply fan, it makes it turn, it goes in lower level, passes through your cooling coil, CDQ again, heating coil, humidification, and discharge. So this slide, it's really just to show you that even though we call this a semi-custom unit, you can get very creative with the amount of components and layouts that you used in a modular semi-custom air handler. And this is that same unit out on site. So as I mentioned earlier, this is what's called a pipe chase on the side of the unit. We actually have two levels of coils here on the top and bottom, and the pipe chase is used to house the piping connections as well as the control valves so they're not exposed to the outdoors and run the risk of freezing or breaking due to the conditions. Here's another example of a unit. So this is a return fan economizer. The return air enters this return air plenum, passes through your return air module. This is the economizer that we saw, which allows the unit to enable free cooling when outdoor air is applicable. Your filters, heating, humidification, cooling, supply fan, filters, and your discharge plenum. This was a unit, a semi-custom unit that we had a lot of enhancements added to it to use in a pharmacy compounding center. So that's in a space where you typically might see a custom unit, but in this particular application, we were able to use a semi-custom with some different hardware enhancements to allow the hospital to pass through.
Okay.
And once again, this is that same unit on the root curb. So this is
tell me,
in Milton, Massachusetts.
we will sign the card to Ernie, and what
Outdoor.
next? I thought
Hey, do you please
I don't know, but I don't know if give it to Paul. Yeah, cause he will be here on Tuesday.
Sorry, ma'am. Whoever's talking on the phone, would you please mute your phone? You're interrupting the presentation. Thank you.
Thank you all. So as I said, this is another picture of that same unit we saw on the previous slide. So if we go back here, you can see your outdoor air hood as well as the windows. Here is when you have a finished project on site. This unit, what we should note is for an outdoor unit, some things you're going to see are ganged latches. So you have one latch at the bottom of the door that allows you to open them up. On an indoor unit, you might have three separate latches. The unit also has viewport windows for you to. But now, last but not least, let's talk about the custom air handlers. These are the most burly units that you're going to see on a project. Custom, they're called that because they're designed in a CAD program, and it allows a design engineer to build an application, build an air handler to meet any type of application requirement. We call these the TCFS or TCPA. They can be sized from 1,500 CFM all the way up to 200,000 CFM and beyond. And a custom air handler is going to be able to vary the dimensions in 1-inch increments, so your length, width, and height. You have different capabilities for your casing thickness, so 2-inch, 3-inch, or 4-inch walls. You can make them out of galvanized steel, stainless steel, or aluminum for different weight requirements or corrosion. You can have fan arrays of up to 18 fans for increased redundancy. So as you see here on this top unit, we've got 3, 6, 9, 12, 15, 18 fans just in this one unit because of the amount of air that needs to move through and the static pressure requirements. You can also have different service and maintenance enhancements, which include service corridors, wash-down capability, which means you can walk into your air handler with a hose, spray it down to clean any contaminants. So in different food processing facilities, we see wash-down construction specified often. You can have knockdown construction, which means the air handler is going to ship completely broken down, almost like a Lego set, and then it can be completely assembled on site by a service technician. So if you have a historic building where you can't remove a facade to get an air handler into the space, or you just have a really tight mechanical room that you need to get your air handler into, knockdown construction might be a good option for you. Another thing would be your motor removal rails. So if you look up here, you have maybe a 10 or 15 horsepower motor that's going to be 5 or 6 feet off the ground. A motor removal rail allows you to use a chain fault to pull that motor out of the unit without having to use an A-frame in the air handler or risk any harm to a service technician. So as I mentioned, custom air handlers are fully custom. They're ideal for any type of mission-critical application like hospital, lab, production facility, any facility where that air handler needs to be online 24/7, 365. This bottom right-hand unit over here is a unit that was used at MIT's nanotechnology lab. So this was one of the largest, most complex air handlers that Trane has ever built because MIT had such strict requirements about this air handler being able to perform in all conditions, no matter what the scenario. So for the same breakdown, if we look at the custom air handling market, once again, healthcare makes up a large percentage of the portfolio because they have such strict requirements on what they can send into space. We also see them used often in industrial settings, 14%, commercial office, 22%, as well as your other commercial 9%, education 17%, and government 8%. And to give you an idea of some of the different reasons you might need to go with a custom unit, this is a unit that was designed to fit in the corner of a mechanical room. So as you can see, the air is going to pass through this tunnel and make a left-hand turn and move out. And this was just because there was no room in a mechanical room to fit a conventional straight-line air handling unit. This slide probably looks like an eyesore, but it's supposed to look like that to confuse you. But this is an entire mechanical room or penthouse mechanical room that was built as a single air handling unit. And when I say a single air handling unit, this unit actually has 4 different air tunnels. So this is a supply air tunnel on the left. We have an exhaust air tunnel in the middle, another one here, another supply air tunnel here, and in between, you have all your intermediate piping, controls, valves, steam generators, things like that. So these custom air handlers can get very complicated very quickly, but it's just a way to show you that they can be tailored to meet any different project application or requirement. And the last I'll touch on, as we have a minute left here, is your packaged DX RTU. When we say packaged, it means all the components fit in a single box, as well as your controls and your cooling source, which is your DX cooling. So as we look at this unit, you have your mixing box, your filter rack, coils, fan, heater, and your compressor section of your condensing unit. Packaged DX RTUs are nice because it's a packaged system, so there's no assembly required or controls mounting. They can come from 1,200 to 65,000 CFM. They have DX cooling with gas, electric, hot water, or steam heat. But the one drawback is that they have limited component flexibility compared to previous units because everything needs to fit in that one single piece box. So they're typically used for constant volume or variable volume applications, things like retail or office space. It's very good for just a basic comfort cooling application, but it will come with less temperature and humidity control than the hydronic air handlers that we saw earlier. So I know we're right at 3 o'clock. That's good. Just about wraps up the presentation. I'll open this up to any questions that you have now, I guess either on the phone or on the public chat. You can send that in there. But once again, I want to thank everyone for jumping on the call this afternoon. Definitely one of the largest presentations I've given. I don't think I've ever had 62 participants at an in-person lunch and learn. So thanks again, everyone. And Tom, appreciate you setting this up for us.
That's fine. If you have any questions, or if you think of a question later on after we close out the meeting, send it to me and I'll forward it to Lou. and get an answer for you. So that's not a problem, okay?
Absolutely.
Also, we're always interested if there are other systems, other technology that you want, you want some training on, then forward that to me in an email, and we'll work on that too. I think Lou and I have been talking a little bit about possibly some other things that Train does put together. We can put something, or we can get into a little bit more detail, maybe on some particulars and things like that. But we'll be working on all that stuff. But we're going to hang on for maybe about 2 more minutes, and if you have any questions, then use the chat to type them in. If we don't hear anything, I'm going to sign off for now.
Thanks again, everyone. I appreciate your time.
Hey, Tom.
Yes.
Is it possible to print this presentation? Because I can't right now, but could we in the future?
Yeah, we definitely can I can get a copy of that and put it on the listserv. I can send it on the listserv, but I can also put it on the DCAM training.
Okay, because I could really use this for some of my people that have limited knowledge. I thought it was pretty good, actually, very good.
Oh, that's great. And who's talking? I'm sorry.
It's Steve Park from UMass Medical.
Oh, sure. Okay. Hi, Steve. Yeah, no,
How you
we can
doing?
absolutely do that.
Okay, that's great. You want me to send you an email tomorrow or something?
Yeah, you can do that. And if others would like to get a copy of that, I can put it on the training webpage, on the MAFMA training webpage, because I have a copy of it. So
Okay.
All right.
All right. Thank you, Lou.
Out of it, Steve.
Thanks for having us. Appreciate it.
Thanks, Steve.
Have a good afternoon, guys. Goodbye.
Okay, folks, so I'm going to be closing out right now. I want to thank you all. Stay tuned on the listserv for future trainings, and like I said, send me any questions that you might want to give to Lou or any suggestions on future trainings. We will continue to be working on that, and I want to thank you all for the time that you gave to us. I know it's always a busy time, but thanks a lot, and we'll see you again later on.